I wonder, yeah, it looks like you should be able to hear me now. Is that okay? Let me know if you can hear me now. Hello, hello, hello. I can see the microphone kind of bouncing. Okay, there we go. Okay, now you can. Perfect. There's about a 10 or 15 second delay, so that's why I didn't respond right away. Okay, so we're going to be talking about number systems today, and I want to be very clear. We were talking about systems of linear equations before, or systems of equations, or there's a few different ways you could describe it. Systems, this doesn't really have a whole lot to do with systems of linear equations, even though it has the word system in it. So we're going to be talking about number systems. These are things that you probably have maybe heard about a little bit. I don't think you guys have sort of really studied this yet. It is part of your grade 9 advanced curriculum, so we are going to cover it. I don't think that you studied this in the first semester. So they should be fairly new, but you've probably heard of some of these topics already. So I think now is a great time to cover it. And the cool thing about number systems is that it leads to many new ideas. And in a lot of ways, okay, Goose, go away. In a lot of ways, number systems are kind of like the foundation of mathematics. You can describe a lot of how mathematics works when you really understand number systems. So it's a really cool topic, one of my favorites. So let's just jump right on into it. So number systems are all about the different types of numbers that we can have. Systems. Okay, so this is talking about types of numbers. Okay, so we use numbers to describe quantity, right? That's what a number represents. It represents quantity, right? So the quantity of something. Now you can have things that have different quantities, right? Like if I just made, or I'm in the process of making bread, right? And with the bread, I was instructed to use 3.5 cups of flour, right? So that's a certain type of quantity, right? 3.5. There's some fractions in there. It's not whole numbers. Now, if I was talking about the number of cats that I have, like this one right here, if I was talking about the number of cats that I have, it would be pretty weird if I said I have 3.5 cats. Like, woo, that's sketchy territory, right? Like, who has half a cat? Well, we really only talk about whole numbers with cats, right? And we'll see that there's some numbers that are just completely incompatible with certain situations, right? You can't describe quantity using certain types of numbers. So, let's talk about the different types of numbers, and we're going to build up on them from the easiest to understand types of numbers to the most abstract and esoteric types of numbers, okay? So, the first number that I'm going to, the first number system that I'm going to talk about is the natural numbers, okay? We're going to talk about the natural numbers. And it's a great place to start because they are natural, and they're called natural numbers because they naturally just come out of observing the world around us. And we've known about the natural numbers for many thousands and thousands of years. So the natural numbers, so this is what they look like. Now I'm going to write a symbol for each of these numbers, and I'd like you to practice writing the symbol if you haven't already. The symbol is kind of the universal symbol that represents each of these types of numbers. So the natural numbers, I write, and why don't I make it really big? So we make like a big N like this, and then on the top left of the N, I start again and I bring it over a little bit, and then I make another diagonal line, and that is the set of natural numbers. And if you want to get really fancy, you can give yourself some serifs here, like this, or even like this if you really wanted to. You don't really have to go that far, but the important thing is that there's two lines in the middle, sort of signifying that this is a bold number. And maybe later what I can do is I can post online what these symbols look like in a computer font. I know, and anytime I teach this stuff, I always go over the font, and it seems like it's a moot point. It seems like it's irrelevant to be talking about fonts. But when it comes to mathematics, you need to be able to write things down, and there's a specific font that's used to write these numbers down. That font is called Math BB, or in other words, Math Blackboard. So I'll just make a quick note that this is the Math Blackboard font, and it's called. Oh, sorry, my cat's just going a little crazy. Oh my gosh. You guys still here? Okay, good. Sorry, my cat just hit refresh on my page. It looks like the live stream kept going. I don't think that I actually need this window up to be live streaming, but yeah, sorry, she just jumped on my keyboard and I hit refresh. So I think we're okay. Anyways, back to the Math Blackboard font, and why is your math teacher talking about font faces? Well, the Math Blackboard font was developed I think sometime in the 70s, and it came because math teachers were writing capital letters to describe number systems, and what they were doing is they were kind of scribbling these big bold numbers to say, okay, yeah, that's a set of natural numbers, because sometimes in math you might want to use the letter n, but n is going to be different than this bold n, which describes the set of natural numbers, right? Like, this is not a variable. This n is not a variable. It is a very specific set that always means exactly the same thing. So we used to just use we would just scribble these big N's, and then we realized, hey, that takes too long. So then to signify a bold letter, we would just do something like this. And then that became sort of the universal symbol for the natural numbers. And then when they started writing math using computers, then they really honed in on it and made it look very specific. So probably on Word. Actually, not Microsoft Word. I don't think that MathBB is on Microsoft Word. The place that you will find this is a typesetting software that is not Microsoft Word. It's the typesetting software that mathematicians use to write papers and stuff. So believe it or not, but mathematicians do not use Microsoft Word. We do not use Google Docs. We don't use any of those funny pieces of software. We use what's called LaTeX. We use LaTeX, and this is how you spell LaTeX. We use a capital L, a lowercase a capital T, a lowercase e, and a capital X. You can look that up. It's the LaTeX typesetting. Typesetting. It's a LaTeX typesetting software. It looks like latex, but it's actually LaTeX. Because this is actually supposed to be a Greek letter chi instead of X. Anyways, I'm really getting sort of off track here. But I really just love talking about this stuff. This is one of my all-time passions, is the LaTeX typesetting language. It's a beautiful typesetting language. It's a lot like HTML. If you've ever done any web design, like if you've ever made a website, then if you know how HTML works, LaTeX works in a very similar way. It's what you call a markup language, not a programming language. It's not for programming. It's for markup, which is similar to a programming language, but it has a completely different purpose. Anyways, the LaTeX typesetting language is where the math Blackboard font was born, and this is where these symbols come from. So you can usually tell what an author used when they're writing books, if they actually use these fonts or not. So I'm kind of using this book as a reference for me. You can tell there is no math Blackboard font, so they probably used Microsoft Word. They did not use LaTeX in this book. So anyways, I'm getting really distracted. Let's get back on track. So this is the set of natural numbers. The set of natural numbers, n, is the set. And to talk about a set, we use set notation. So to open a set, we use a curly bracket like that. So I'll just make sure that my curly bracket looks perfect. I don't usually care that much, but maybe you've never seen this symbol before. So I want to make sure that your initial reference is right. So it's kind of like a vertical line, except it sort of has a curl on either end and then a little bump in the middle. Okay, and this is the set that starts with the smallest number in the set is 1, and then it just goes up by 1. So these are all what we would refer to as counting numbers, right? These are the numbers that we use to count things. Like, how many cats do you have? I've got 2 cats. That's a natural number. So this is usually referred to as, so sometimes we would refer to these as whole numbers. Sometimes we refer to them as counting numbers. Okay, because we use them to count things. We use them to count whole things. There is some sort of, some people say, okay, well, whole numbers include 0. And I have to be honest with you, this is not consistent. If you look in different books, different people say different things. The natural numbers, sometimes people say that the natural numbers include 0. Some people say they don't. It's not, like, this is the one area in math that as far as I can tell, there's different schools of thought. And some people say, you know what, 0 is a natural number, because in set theory, that's an area of math called set theory, where you talk basically about just this stuff, the different types of numbers that you can have. In set theory, we have this thing called the empty set, and the empty set has no elements in it. It's like it's like an empty bag, right? It's saying, okay, you can have a bag, but the bag is empty. And some people say, okay, because there's the empty set and the natural numbers are built off of set theory, then 0 should be a natural number. So some people say that 0 is a natural number. Some people say that the whole numbers are like the natural numbers, but they include 0 as well. But I don't talk about whole numbers. I kind of take a more of a traditional approach with the natural numbers, and I just say the natural numbers are these numbers. And if it was up to me, if I really was teaching this course, I mean, I'm kind of using a bit of a guide here, so I do want to be consistent with this guide. But typically, like, if you ask me personally if I believe that 0 is a natural number, I would say yes. I would say 0 is a natural number, and I would say that because of set theory, because set theory has the empty set. A big part of set theory is the existence of the empty set. The empty set has 0 things in it, so 0, I believe, should be a natural number, but that's neither here nor there. The important thing is just to understand that the natural numbers are just whole numbers. They're all positive. So the cool thing about this is that you can kind of see the history of mathematics sort of unfold when you talk about the different types of number systems. Because like 10,000 years ago, like, we still had numbers. Like, we knew how to count. We've known how to count for a very long time. However, we didn't have the existence of 0. We didn't know about negative numbers until later. Okay? So the next number system is the set of integers. And integers is a big topic. It's a huge topic in grade 7 and in grade 8 to start learning about integers. So you've probably heard about integers before, and what you may have, like, if I asked the class right now, are we going to count 0 as a natural number? For now, no. we are not going to use 0 as a natural number. For now, we're going to say 0 is not a natural number. But even though, if you ask me, I would say yes. In this instance, the answer is no. 0 is not a natural number. But just know that some people disagree. Integers. Integers are up next. Now, if I were to ask the class what integers were, I think that about 80% of you would be on the right track, but you might be off a little bit. So integers are the next number system, and the way we write integers is in the following way, and I'll make it nice and big. So we draw a big Z like this. Okay. Well, I guess I shouldn't say a Z. It's more like a 7. And then we start again from this corner, but not right in the corner, but just right beside the corner, and then make another sort of upside down Z. So it's like 7. So it's like a 7 and then an upside down 7, or I guess that's backwards, so it should be like this. So you make a 7 like this, and then another backward 7, and it sort of makes a Z with a really thick line going down the middle. And if you want to get really fancy, you can add a serif. If you didn't know, a serif is the sort of like the ticks on the end of letters and numbers to make them look fancy. Some fonts, like Arial, are sans serif. They have no serif. But a font like Times New Roman, you probably know that font. It has serifs. The tips of the letters, they have those little curls. Those are called serifs. So if you want, you can add a serif right here and here to make it look super fancy. That is a Z. And the reason why it's a Z and not an I is, as far as I understand, and I'm not a linguist, but as far as I understand, the German word for number starts with a Z. I think that's the story that I've been told. I should really look into that though. So don't take my word for it. Look it up if you want. Like, why are integers described with a Z? And this is the set. So it's the set that is pretty much the same as the natural numbers, but it's like there's like a mirror image. It's like there's some symmetry. So now we have negative numbers. So there is no smallest integer. There's no smallest integer. So when we write it, we start off with dots. So we go off starting from like negative infinity, you can think of. So we're going off from that direction, and then we have -3, -2, -1, oops, and then 0. 0 is an integer. There's no, and everybody believes that 0 is an integer. There's no dispute about that. 0 is absolutely an integer. And then we have +1, we have +2, we have +3, and then we keep going. Okay, so those are the integers. That's the set of integers. So these are, the way we can sort of think of them is we have like their whole numbers. Okay, 0 is included, so 0 is included. And also we have negative whole numbers. Okay, negative whole numbers. And I should also point out that sometimes it's useful to talk about what numbers are not in this set. So some of the numbers that are not in this set are, well, we have no decimals. No decimals or fractions, okay? Unless, I mean, like you could say like, okay, -3 is like the same thing as -6/2, right? It's technically a fraction, right? But you can think of any fraction that doesn't reduce to a whole number, right? So there's no fractions, no decimals, and I mean, in a similar way, you could say, oh yeah, well, -2, that's the same thing as -2.0 decimal, right? Okay. Sure, there's some fractions and some decimals, but no fractions or decimals that's simplified to whole numbers, right? So, so that is the set of integers. So I think when I said that about 80% of you would be on the right track, I think that a lot of people think that integers are just like maybe there's negative numbers too, right? Like, so I think a lot of people think that integers mean negative numbers. Not true. Integers is a very specific set of numbers. It's the whole numbers with 0 included and negative whole numbers as well. Okay, so are we going to count 0 as a natural number? No, we are not going to count 0 as a natural number in this class. Negative numbers. Aha, see, look at that. I called it. I thought that a lot of you would think that integers were negative numbers, and here's someone in the chat said that integers are negative numbers. Isn't there some set before that? Not really. Can you post this online? Yes, I'll put some stuff online. I'll put a little PDF together online. I'll put it on the website. Do the natural numbers have fractions and decimals or no? No, the natural numbers, it's just like let's do a little test. Like, is 0 a natural number in this class? No. Is 6 a natural number? Yes, it is. Is -2 a natural number? No, -2 is not a natural number. Is 1.5 a natural number? No, it's not. Is 2/3 a natural number? No, it's not. So we're going to go over some examples like that pretty soon. Okay, so that's the integers. Rational numbers are next. Ooh, this is where it gets interesting. Okay, so I've got integers, and then I've got rational numbers. Rational numbers. Okay, so rational numbers, these are next. Okay, now rational numbers, I'm just going to underline sort of the key word here is, or not so much the word, but part of the word, ratio, okay, or like rational in that numbers that can be written as a ratio. Okay, so these are numbers that can be written as a ratio of integers. Okay, so the way we write this, and I'm going to write this in the most formal way that I know how. Okay, it's a very specific formal way, and the reason I'm doing this is twofold. One, it's good to have this written down so we can be very specific and clear. But two, I also want to sort of give you a sneak preview about some of the topics that you'll be learning about next year, in particular set notation. In other words, how to write sets down. Okay, so it's a big topic on how to write numbers, or how to write sets down in a way that is clear and consistent and concise. So without further ado, let's talk about the rational numbers. Now the rational numbers, we use the Math Blackboard font again, except we use the letter Q. So I'll show you how I write it. So I start off at the top and I go all the way down. I do a big O like this, okay? And I keep going until I hit about this point right there. And once I'm here, then I make a vertical line down like this. And then once I hit this side, I kind of bounce up like this, whoosh, like that, okay? And there's my Math BB or Math Blackboard Q, okay? And the reason why it's a Q and not an R is because Q stands for quotient. Quotient. And if you remember, quotient means the answer to a division question, or in other words, a ratio, right? Because it's a rational number, okay? So we're using quotients. We also don't use R because another set that we're going to talk about is the set of real numbers. The set of real numbers. Okay, just give me 1 second here. Just have to check something out. Okay, pardon me. just had to look something up real quick. Okay, so this is the set of rational numbers. So this is the following set. Okay. So I'm going to write this in a way that might look a little confusing at first, but I'm kind of sharing with you a sort of a type of a language and the way that mathematicians write sets down. Okay, so a set, if you didn't know, is a collection of objects. Usually in math, the objects are numbers, but a set can actually hold anything. So it could be really anything. So these sets have numbers in them. So the way I'm going to write it down is that I'm going to say that Q is the set A over B, okay, such that, and I use a colon. Some people use a straight line, a bar. You could use either. I prefer to use a colon. Okay, so it's the numbers A over B such that, so this thing right over here means such that. So I'm clarifying. So it's A over B. What's A? What's B? What are you talking about, right? Well, that's what the such that is for. A over B such that A and B are elements of the integers. So this really means A and B are integers. A and B are integers. And I have to include one more really important point. B is non-zero, okay? And that's the whole set. The reason B can't be 0 is because we're dividing by it, right? You can't divide by 0, okay? So this is the set of rational numbers. Basically all, like, take any two integers except for 0 being on the bottom. So take any two non-zero integers, divide one by the other. That's what a rational number is. Okay? So this has, so all fractions. Actually, I'm kind of running out of room there. So let me rewrite that. So this is all fractions, and let me zoom out here again here. There we go. Okay, that's better. Okay, so this is, and I'll change the color as well. Okay, so this is all fractions, and it's also all decimals with either terminating decimals. Okay, so terminating decimals, that means something like 2.51, right? That decimal ends, boom, 2.51. We're done. No more talking about 2.51. And also repeating decimals. Decimals. Okay, so we've got terminating decimals like 2.51, and then the decimal's finished. And we also have repeating decimals like 3.21 repeating, right? Like this would be 3.21212121 ... right? So all of those, that's what the rational numbers are. So you could have like I'll give you an example of a fraction, right? Not that I need to, but 2/3. That would be a rational number, right? Because it's a ratio. It's the ratio of two numbers. It's the ratio of 2 and 3. That's what a rational number is. And all of these, the way we think about it in terms of decimals, well, I'm hoping that we can take a fraction and convert it to a decimal, right? I believe that's something that you would have done in grade 7 and in grade 8. So yeah, a fraction you can always convert to a decimal, but only certain decimals can you convert back into a fraction, right? So you can certainly, like this 2.51, I could say, well, 2.51 is 251 over 100, right? That's what that decimal is equal to. So it's a fraction. And maybe I'll show this to you tomorrow. I don't know if you know how to convert repeating decimals into fractions, but and I can't do this one in my head. So, but this is, I can write that as a fraction, okay? And that's why it counts as a rational number. So you might say, okay, well, isn't that all the numbers? Like, what's not in here? So not in Q. The numbers that are not in Q are irrational numbers. Irrational numbers. Okay, well, what's an irrational number? Well, we'll talk about that next. So that's a decimal number. It's a decimal. It's a decimal that does not repeat. Doesn't terminate. So it keeps on going on and on forever. Doesn't terminate. And doesn't repeat. And the go-to example, like the most well-known irrational number, is pi. Okay, like 3.14159, blah, 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 right? It goes on and on and on forever and has no repetitions. Okay? So that brings us to our next set. Okay? And this number system, it's not like really a number system that, I mean, here's the thing about these number systems, is that they have these beautiful mathematical properties. So if I take two natural numbers and I add them together, I get another natural number back, right? Take any two natural numbers, like 2 and 3. 2 plus 3 is 5. 2 times 3 is 6. Both of those are natural numbers, right? Same with the integers. I can add them together, and I take any two integers together, I add them together, I get another integer back. I multiply them together, I get another integer back. Now, I can't divide them. I mean, right? Because 2/3, 2 divided by 3, both 2 and 3 are integers, but 2 divided by 3 is not. So I'm not talking about division, I'm just talking about addition and multiplication, which are kind of like very fundamental operations in math, right? Addition and multiplication. Almost everything can be described with addition and multiplication. So I take any two natural numbers, add or multiply them together, I get natural numbers. If I take any two integers, add or multiply them together, I get another integer back. I take any two rational numbers, add them together, I get another rational number back, and I get and if I multiply them together, I also get a rational back, right? Think about it. You take two fractions, multiply them together, you get another fraction, right? That's how it works. With irrational numbers, this is not true. Okay, so this is why, like, irrational numbers, it's not actually really a number system because it's not what we would call closed. It's not a closed number system. So we don't, like, mathematicians don't usually talk about irrational numbers. It just helps you learn how irrational numbers work. So some people call irrational numbers P, right? Kind of like how we called rational numbers Q. I'm not gonna, like, they don't, like, mathematicians don't actually consider irrational numbers as a system because they're not a system. Because I can take two irrational numbers, I can multiply them together, and I can get a whole number. I can get a natural number back. So, which is not irrational. So I'm gonna just tell you what an irrational number is. So irrational numbers are next. I think I was using blue. Okay, irrational numbers. And capitalize that, irrational numbers. Okay, let's talk about irrational numbers. So what are irrational numbers? So these are numbers that cannot be written as the ratio of two integers. Okay, so any two numbers that cannot be written as the ratio of numbers. Sorry, any number that cannot be written as the ratio of two integers. So an example of that would be pi. and pi is equal to 3.14159, blah, 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 and so on. There's when you write them as a decimal, so you can't write these as a fraction. These don't exist in the fraction world. They only exist in the decimal world. So when you write this, there are no termination of decimals and no repetitions. Okay? So that's what makes it irrational. So basically the way the word works is that there is no ratio. Ir meaning like no, and ratio meaning ratio. So there's no ratio that you can use to express that value. Another example is the square root of 2. Okay? So this is equal to 1.41 blah 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 blah, and there's no repetition. So a lot of square roots will give us irrational numbers, and we could invent our own value. Like I could have 0.10 100 1000 1000 1000 10000, and so on. Here's an important thing. Here's a very important thing. Some irrational numbers have a pattern, right? So here there is a pattern, right? The way I wrote this is that there's 1 0. Here there's 2 zeros, here there's 3 zeros, here there's 4 zeros, and here there's 5 zeros, and so on, right? There's a pattern, but just because there's a pattern doesn't mean it's rational. There's no repetition. Nowhere do we have like an infinitely repeating pattern, right? So there's a pattern, there's a pattern, and there's some small repetitions, right? Like if you look very closely, like, okay, here's a 0 0 followed by another 0 0, right? There's some repetition. But what I'm talking about with a repetition is like infinitely repeating. So like 5.212121212121212121, right? And it keeps on going on forever as 21212121, right? Whereas this, it doesn't repeat itself. Okay, so we're kind of running out of time here, but that's okay. I'm almost ready to give you your exit slip. Going to be a very simple exit slip today, just to keep things straightforward. But we're now going to talk about the real numbers, the ultimate set of numbers. Okay, so the real numbers. This is the best number system. Okay, this is like the be all and end all of number systems. And turns out that there's actually one that's a little bit better than real numbers, but we don't really need to talk about that number set until much later. I'll mention it tomorrow, or not tomorrow, I'll mention it on Friday. I'll talk about the one that's bigger than real numbers and a little bit cooler. There's a lot of interesting stuff that happens in that set. But for now, the real numbers it's like the catch-all. It's pretty much everything. Okay? So we have natural numbers, naturals. We have the integers. Okay, we have the rational numbers, and we have the irrational numbers. Okay? So what I'm going to do, I'm actually going to say, okay, let's just for now, let's just call the irrational numbers P, even though they're not like a real number system, because they don't have this nice thing. By the way, what I was talking about is that the square root of 2 times the square root of 2 is equal to 2. That's what I was saying before. So that's why this is not an actual number system, because it's not closed under multiplication. So I can take two irrational numbers and I will get a rational number. So that's why it's not really a number system. But let's just call it P, and then that way we can say that the set R, which is the set of real numbers, this is the set Q union p. Okay? And that's the best way to describe the real numbers, is that it's all the rational numbers and the irrational numbers combined. Okay? So what does that mean? So let's just take a second to talk a little bit about the notation that I'm using. So this is a union, and it means combine. So we're going to combine these two sets into one big set. Okay? So a union is where you take two sets and sort of join them together. What's the math BB and set for the irrational numbers? Yeah, I just told you now. So it's P. But just keep in mind, please keep in mind, the irrational numbers is not a number system. Okay? It's not a number system, because when you multiply two irrational numbers together, you get a rational number back. So the real numbers, that's everything all together. It's like all the numbers you can think of, all in one beautiful set. So that's this system. So like 2 is a real number. By the way, this little guy, this is element of, which means like this means is a real number. Is a, like 2 is a real number. It's a Greek letter epsilon, or some people call it epsilon. I call it epsilon. So that's the Greek letter epsilon, and that means 2 is a real number. We could have 2.1 is a real number, right? We could have 2/3 is a real number. We could have the square root of 2 is a real number. We have that pi is a real number. And you might say, well, what's not a real number? This is everything. Like, it's the whole thing. Well, yeah, that's the whole point. That's why it's called the real numbers. The only numbers that are not, so let's say, what isn't a real number? What isn't a real number? Well, what isn't a real number is the following: the square root of -1. That's pretty much it. And then the square root, basically the square root of negative numbers. Okay, that's pretty much it. Any other number is real. As long as you're taking the square root of a positive, you're good. The only time you get values that aren't real numbers are when you have negative numbers. Also, if you divide by 0. So divide by 0. Dividing by 0, that's not a real number. In fact, that's not a number at all. It's not even defined. So yeah, there's that. And then you have these weird things like 0 to the power of 0, infinity. These are all sort of like, what the heck are these, right? So these are not real numbers, but pretty much everything else is. Like, anything that you can really think of is a real number. Anything that has, like, if you can write it down, it's pretty much going to be a real number. So you've got whole numbers, you've got decimals, you've got fractions, you've got positive square roots, you have pi, and there's another really important number, e. That's Euler's constant. Okay, Euler's constant is a real number. So if you can write it as a decimal, it's a real number. Even if it's a non-repeating, non-ending, non-terminating decimal, it's going to be a real number. So exit slip for today. Okay, so the exit slip for today, let's see. Let's say, okay, I'm gonna look through this book, see if there's any good questions here for you. Okay, here's one. Yes or no, true or false, okay? True or false. Okay, true or false. 2.313131 repeating is a rational number. Okay, that's your exit slip for the day. Is this a rational number? And that's it. Okay, so we'll talk more about this tomorrow. I keep saying tomorrow. Friday. I'll talk more about this on Friday. We'll do some more examples. We'll talk about how these sets are related to one another, because they actually do have very close relationships with one another. However, we're out of time, so I'm gonna sign out. So I'll talk to you guys Friday. Have a good rest of your day. No homework for today. There's really the homework for this stuff. It's kind of it's hard to assign homework because it's really just kind of like true or false questions. Like, is this a real number? Is this a rational number? So no homework for today. But please do the exit slip, and I'll talk to you guys Friday. Okay, bye bye.